All right, so problem number 55, it says there are 4 identical masses and each are located in corners of a square with 1 meter sides. Then it asks us, what is the net force of any one of these masses? 4 masses, and we're just going to assume that they're spherical, and they're identical masses, so they all have the same amount of mass. Okay, and so we'll call this mass 1 and mass 2, but they all have the same mass, and we'll just identify that as M. All right, now what they're really asking us is what force is being applied to all of the masses at any one particular time. So now here's the thing, if I take this blue mass, there are 3 masses acting on it from a gravitational perspective. There is a gravitational pull towards that mass, there's a gravitational pull towards that mass, and a gravitational pull towards that mass. And if you rotate through the picture, it's the same type of pull on the other 3 masses. In other words, each mass has 3 masses acting upon it. So what I could do is I could, and the way that we find the mass, so let's label these. Let's call this force 1. Let's call this force 2. And I didn't draw the vectors quite to scale. In reality, they're not quite that far up. But I just drew it to kind of show you what they're being pulled towards. Okay? So those are the 3 masses. Well, the formula to find the force between 2 objects is on page 257. Okay? And the force between 2 objects is, the force due to gravity is equal to the gravitational force constant, or the gravitational constant G. And normally in your book it would be like mass A times mass B all over the distance between the 2 of them squared. Right? Okay. So now, the distance, according to our textbook, this square was 1 meters on every side. The distance from them is 1 meters. So, if I wanted to see how force 1 was, what are the 2 masses? Well, force 1, I have the gravitational constant G, and then I have this mass, which is M, times this mass, which is also M, all over the distance between them, which is 1 squared. Right? You guys see that? So then I have the force between here is G M squared. That's it. Now, it's the same thing. If I did that exact same thing for F sub 3, I get the exact same answer. Right? What's different? Well, the difference is the distance for F2. When I go to do F2, the distance between them is different. So I'm still going to have the gravitational constant G times the mass, right? Because this mass is M and this mass is M. So the masses don't change. But the distance between the 2 of them do. Now we could calculate this, or we could use our knowledge of trigonometric functions and the right triangles. If I were to take the section out, I have a right triangle where this length is 1 and this length is 1. What is the hypotenuse or the diagonal? Square root of 2. See, we know that because it's a 45-45. So we know that that's the square root of 2. So what's the distance between these? What's the distance from here to here? Square root of 2. So the only thing that changes is that F sub 2, the force that this particular mass exerts on this mass is g m squared over the square root of 2. Now, technically from a math perspective, we should probably rationalize the denominator. And we would do that. Oh, and that has to be squared, by the way, right? That has to be squared. So it's really just going to be 2, right?
Yeah.
All over 2. Okay? So, if we were to plug some numbers in, we would see that f sub 1 is equal to f sub 3, which is equal to the gravitational constant, 6.67, times 10 to the negative 11, times the mass of the object. And did they give us the mass? I kind of got ahead of myself and didn't read up the problem all the way through. Seems to me that they gave you the mass at the, oh yeah, it says the mass of the object was 2.5 kilograms. So each one of these had 2.5 kilograms. So this is 2.5. So F sub 1 is equal to F sub 3, and that was equal to 2.5 times 6.6 times 10 to the negative 11. So let's do that on a calculator. I've got 6, whoops, got to put my marker back. I've got 6.67 e to the negative 11 times 2.5 kilograms. I got 1.66. Oh, but I've got to square that, don't I? This has to be squared. Why aren't you guys catching this mistake? Jeez, you guys, I can't do everything. All right, so I'm going to say 6.67 e to the negative 11 times 2.5 squared. All right, that's better. Whew. So this is about 4 point, what was it?
16875.
Let's just round that to 4.17 times 10 to the, was it negative 10?
Yeah.
Newtons. Now I'm going to take that same number and now divide it by 2, right? Because that's the same number, but now we're dividing by 2. So f sub 2 is this divided by 2, which is about 2.8 times 10 to the negative 10 newtons. So now here's the thing, I don't know if you guys realize this, but because by symmetry, because this is pulling this way and this is pulling this way, because this is, well, let's draw it on another picture because we got a bunch of numbers there. So let's start over, picture-wise. You don't have to draw a new picture on yours if you don't want to. We don't need to talk. Delete. All right, so what I have is I have a mass here, I have a mass here, I have a mass here, and I have a mass here. And what I've done is I've calculated that this force here is equal to this force here, and they have the same magnitude, which is 4.17 times 10 to the negative 10 newtons. And I have the same one here, which is 4.17 times 10 to the negative 10 newtons. And if I use the tip-to-tail method, guess what? If I use the tip-to-tail method, the resultant vector of these two would look like this. And the way that I would get the resultant vector, this force, the resultant force, is equal to 4.17 times 10 to the negative 10 squared plus 4.17 times 10 to the negative 10 squared. And we take the square root of that. But then on top of that, I'm going to have another vector, which was my f sub 2, which was, what was that number again? 2.08
Yes.
times 10 to the negative 10 newtons. So what is the overall force acting on that mass? The sum of the blue and green vector. So now if I crank through this and I plug this in my calculator, I could write it like this too. Couldn't I do this? Could I say 2 times the quantity, 4.17, right? Times 10 to the negative 11 squared. Oh, was it negative 10? I'm sorry. A lot of stuff going on here. Good job. And then what I want to do is I want to add the 2.08 times e to the negative 10. And I get 7.97. And if I were to round that, what would you guys round that to?
8.
8. So if I take that, the total force is 8 newtons. So the total force is 8 newtons. So what this means is if I were to draw like a free body diagram of all the forces acting on these, I have this mass here, and this mass here, and this mass here, and this mass here, and each one of them has a resultant vector force of 8 newtons towards the center of the square. Does that make sense? Was that easy?
No.
No.
If you don't press.
All right, so let me recap. We'll do the recap real quick, and then that'll give you a chance to make sure you've written everything down. So originally we started off with 4 masses equidistant from each other on the corners of a 1 meter square. And what we did is we cranked through, we did a bunch of math, but what we found, yes, God bless you, what we found was that there are 3 masses acting on 1 mass, which means there are 3 forces. We calculated those forces. We found that 2 of the forces were equal because they were equidistant. So when we cranked through and found all the forces, to kind of clean up our page, what we said was, well, let's combine all the forces and add them all up. So what we did is we said, all right, we have 2 forces that are the same but in different directions. In other words, they're both 4.17 times 10 to the negative 10 newtons. And then we have a diagonal force that was 2.08 times 10 to the negative 10. But if we add up all the forces, the resultant vector of the 2 smaller forces was actually 5 point something, right? Alright? So this one here, my resultant vector in green was 5.89 or 5.9. So this one here was like 5.9 newtons. Well, if I took that number and added it to this number, that would give me the total force. In other words, what we're doing is, if this was vector mathematics, that's the total force and the direction acting on just this little lonely particle. Okay? Any questions?
Mr. Adams, what
Yes.
about you 8 to the negative 10 newtons?
Oh yeah, I forgot the order of magnitude, thank you. I was just so excited that I didn't make any mistakes when I calculated it on the calculator. Thank you. Yeah, it's 10 to the negative 10. Thank you for correcting me. When you do a lot, when Mr. Adams tries to explain the vector math and stuff, I get so excited when I get the right answer that's in the back of the book. Okay? And I suppose we should probably clarify that on the notes over here too, right? This is, all of these are times 10 to the negative 10, times 10 to the negative 10, times 10 to the negative 10, times 10 to the negative 10. It seems like a small number. Any other questions?
No.
No? Okay, good.